Just started the recording. I was talking about the exam. Uh, Reminder. So exam exam two. I think is due today, right? The take home part. Okay. So exam three. Exam three next week. Next week Friday, which is week 11, lecture 3. Okay. And the syllabus is chapter 14. So chapter 14 does have few homeworks. Homework number 7, you guys just submitted, right? Homework number 8 just uploaded, is also with that same thing, right? Okay. And the theory is pretty straightforward. In chapter 14, what did we learn? We learn about the energy, right? Energy and work. And we have this thing continuation here on this problem that you're seeing here. It's a spring problem. We've done one spring problem already, right? So this is kind of similar. It goes with energy conservation. You guys are familiar with energy conservation? We took the thermo already, or at some point we're going to take it, right? Thermo is based on energy conservation. Now it goes with everything in the world. So energy conservation in this particular problem could be assumed like this way: kinetic and potential energy at any point should be equal. Okay, so at point A and B, if you're going to think this way for the spring, so at point A and B, kinetic and potential energy must needs to be balanced out. Okay, we'll talk more about this problem, but before we go any further, if you guys remember, what is the energy equation for spring? Anyone remember? Perfect. That's the equation that we'll be using today. And obviously, you guys remember the mgh is the potential energy, right? And the kinetic energy is half of mv squared. So we're gonna use these 3 equations obviously today, right? This is the kinetic energy. So the goal is, like, today we'll be doing this problem. Friday we're gonna Wednesday we're gonna be doing I didn't say the exam is week 13 lecture. Day 3 could be on day 1 as well, but I guess the way we can do it, like, today maybe we should be doing this exam on day 1 on Monday. Is it too when do you have exam on Friday, right? Monday would be too close. Friday is perfect, I guess. So in that case, I gotta do the review on Wednesday next week. So exam review, exam review, exam 3 review Wednesday, week 11 lecture 2. All right, so I guess, like, the idea over here would be, let me focus on that. All right, so idea here would be, we'll be doing this problem today, right? And then another one on Wednesday, and on Friday we'll be doing homework 8 hits. So you shouldn't wait for until Friday to come to do this homework 8 hints. You should be started solving it and possibly finish it with some questions. Okay, I'll still go through all the questions as much as I can on that day, but there's a plan. And next week, at beginning week 11, we're going to start chapter 15. Okay, so let's start. I was talking about this energy balance, like energy conservation. Let me write something here. So energy conservation. Which in this case, energy at any point should be equal energy at any point. So energy in, energy out. This is a generalist equation. Okay, so let's start reading the problem. All right, so on this problem here, it says By the way, this material is in bright space for access of everybody, right? All these materials. I should have like chapter 14 already. Chapter 15, I'm gonna put it there. So a 4 kilogram collar, C. So this is the collar. If I'm gonna make it a little bigger and you start writing it, the writing get distorted. So let me make it bigger. You understand it? Then I'm gonna zoom it in and then we'll start writing. So a 4 kilogram collar C, this is the collar that they're talking, has a velocity of 2 meter per second at point A. So when this is located at A, it is a velocity at 2 meter per second. The spring constant value is given for this spring that you're seeing, 400 Newton per meter. Okay, the unstretched length of the spring is 0.2 meter. Okay, so unstretched length is at point C. Okay, that is 0.2. But if you're gonna think this way, so this spring is here, right? And this spring, when it is coming like this, so when it is coming like this, the length become 0.1. What does it mean? The spring is in compressed state here. Does it make sense, everyone? And the same spring when it goes here with the collar, obviously the collar is here. Last night the heater was turned a little low, so my sounds may sound a little heavy. All right, when it is at location B, right, like something like that, you see that distance was not directly given, but you can find that distance. How? They have some distance like this. Radius of the curvature is given as what, like 0.4. I'm gonna draw another free body sketch and we're gonna put everything over there. For now, just try to understand. So this is 0.4 meter and this is what, like you have an idea, right? It should be 0.3, right? Because from here to here 0.4, so 0.4 minus 0.1, let me put it this way. So this is 0.3 meter. All right, now from Pythagorean we know if this is 3, if this is 3, this is 4, this is 5, you know that, right? Because it's like, 3 square plus 4 square. The same thing goes here. So this unstretched condition, this would be equal to 0.3 square plus 0.4 square, which is 0.5 meter, right? So you get the idea. So like at position A, the spring length is 0.1. At position B, spring length is 0.5. Okay, try to understand that first. Okay, I'm seeing some of it taking notes. I mean, if you need, as I'm saying, like I'm gonna draw it neatly, and you'll have the opportunity to do it too. But try to understand it, whatever they have explained here on the sketch. All right, let me still read through this. It says unstretched condition and then A, B, and everything. Then it says find the velocity when the collar is at B. Okay, so basically you gotta find the BB. If you're gonna zoom, what is BB? BB is the velocity at point B, right? And the way is very simple, as I'm saying, like conservation of energy, right? What does it says? At point A and point B, you have these 2 points, right? A and B. You would be applying all the energy involved at point A and point B, right? And this time here is not kinetic and potential energy. We have the spring, right? As well as we have the weight of the collar, right? So this problem is a little tricky. And think this way: when the collar is at point A, okay, you understand what is going on here, right, everybody? So think this way. See, the collar is on a guided route or guided tube, I can say. The collar is moving on a tube, right? So it's like guided by the tube, right? It can't go any further. It goes along the tube. Does it make sense? So when the collar is on the top, when the collar is at the top, it can hold by what, Arlene? By the tube, right? It can hold by that, right? So there is a gravitational force acting on the tube always, right? Anywhere, right? But that gravitational force is going to get nullified by what? The normal force. Make sense? Everyone understand this? So when, see, zoom this, this is the collar, right? And when the collar is on the top of this, it has a force due to gravity acting down, right? same time it has a same and equal opposite normal force acting up. So you're going to nullify each other. It makes sense? That means when we are at point A, at location A, we can ignore the gravitational force. Makes sense? What are the components here then? Two components. One is what? The spring. The spring force, right? Half of k x squared. And you talk about it, right? The other one is, does the block has any movement at point A? It does, right? All right, so yeah, you just say that way, right? So it should be like half of m v squared because of the movement. V is the velocity. Anyone understand? Then you got it, right? That's the point A. Why the gravity will not gonna be there? Because the collar is on the support, right? So the gravity is gonna get nullified by the normal force. But the reason I'm emphasizing that, but when the collar is at point B, what happened here, right? It has like free fall, right? So the gravity is gonna come in play here. Makes sense? So not only gravity, what about the spring? The spring is there as well, right? The spring force half of kx squared. And the velocity as well, right? At that point. Do you understand? So at point A, you have two energy, right? Energy means when I'm saying the energy, it has like, it could have work or the energy and whatever the way, but it is the energy, right? At point B, how many? 3, right? Does it make sense? Everyone understand that, right? So yeah, that's the reason. It's not necessarily always at different points when you're doing energy conservation. It's not necessarily always like summation of kinetic and potential energy, right? There could be other components come like here, spring comes, so spring forces needs to be accounted. Does it make sense? Okay. And depends on the situation, bottom line. So that's what the theme of the conservation of energy. As if like you are at different position. You are doing the conservation of energy means you're adding all sorts of energy involved at that point, right? Both at point A and point B. Okay? You got it, Alain? Didn't you got it? Gavin? Perfect. Joe, you got it, right? Okay, so let's start. Let's start with the free body diagram. So we do have this thing. If you're okay, let me keep those. So let's do a free body diagram. Oh man. Thank you. Free body diagram. What does FBD means? Free body diagram. Thank you. So this spring, okay, from two different positions, right? We have seen that. So from one position, the spring got stretched and it does come here. In another position on the top at position A, it is like this, right? So we have all this distance. So from here to here, okay, so from here to here, this distance is 0.1. Okay, from here to here, this distance is 0.3. Okay, so this one you can say this is SA, which is again 0.2 minus 0.1. 0.1 meter. That's the amount of stretch happened on the spring, right? The spring on a stretch condition 0.2, right? Okay, so then you have this length here. So for this length, it is 0.5. And the way you found it is 0.3 square, 0.4 square equal to 0.5, right? All right, so then this is your point B, and that's your free body diagram. And you can say, okay, this length from here to here is 0.4 as well. You need it. So what are the givens here? Let's deal with the givens. So the givens are the mass of this collar, they said, is 4 kg, quite a big of a mass for a collar. Okay, then you have this velocity at point A is given as like 2 meter per second. You have this spring constant is given as 400 Newton per meter. You have this spring on a stretch condition, the X spring 0.2 meter, and you are trying to find the velocity at position B. Okay, taking the class nurture. All right, so let's start the solution. So conservation of energy. Now the spring force, the energy that it creates is actually part of the potential energy. Okay, remember that. The potential energy other form is mgh. Remember, like mgh is the gravity induced energy. Okay, didn't I got it right? Gravity is mgh. You remember that equation, right? Mgh, do you remember that? Mgh, you know, half of mv square. No, Christian, you remember that? Yeah. Mgh, half of mv square. Those are the basic equation. Okay, probably you learned it in high school. All right, so let's start. Potential energy, conservation of energy. So you have this TA plus BA. Okay, so this V, don't get confused with the velocity, is the kinetic energy. That's why you have a line at the bottom, okay? Plus equal TB plus BB. So you can start writing this equation. Now, again, as I'm saying, like the kinetic energy is the velocity, and the potential could have like the spring energy and the gravity energy. Okay, so this is the equation that's from the conservation of energy. Now I'm gonna start writing things like so. Okay, you have this potential energy. This equation is you have this point A. So at point A and point B. Now you guys remember at point A, how many energy, potential energy? Is it 2 or 1? Point A, does it have any gravity? No, it doesn't, right? So you're gonna simply write this VA equal, okay, half of K S squared. Now what S we are referring? As A, right? So you can say this way as A. So it can be further written as half of 400 Newton per meter. That's the spring constant. 0.2 minus 0.1 square meter square. And if you're going to do the math, you're going to have the value of 2 Newton meter, or this is the same unit as joule, right? All right, at point B, find this spring energy. So you can say spring energy. So again, don't get confused with this V and velocity. This V is a symbol that we use for potential energy, right? So VB again for gravity, right? There's two form at point B. We know gravity is mgh, and the spring one is half of ksb square. All right, so question is, how much of a stretch happened at point B for the spring? The spring initially is at 0.2 unstretched condition meter. At point B, how long the spring become? 0.5 meter. So how much stretch happened? 0.3 meter. 0.5 minus 0.2. You understand? So that is your X or SB here. Okay, 0.3, which is again 0.5 minus 0.2. 0.5 is, you can see over there, the spring stretched up to 0.5, and initially without unstretched condition it is 0.2, right? So that's the difference. Understand? Got it? Alright, so then 0.3. Everyone understands this is 0.3, right? So this 0.3 K, what is the K value? It's 400, given, right? So you can find this value. Can you find this one as well? MGH. See, what do you think about it? What will be the value of the H? So H is the distance between point A to point B. What is the distance between point A to point B vertically? Vertically. 0.4, thank you. That's the distance. Everybody got it? I didn't understand why the, yeah, so that's 0.4 is the distance from point A. So this H that you're seeing here for the potential energy at point B, this H is 0.4 meter. Okay, the G is GM is 4 kg, right? Can you do the math? Find those values. Should be getting the values of those two. One is 18, and another one is close to 18 as well, 15.969. So see if you can find it. Okay, now that you have everything, can you solve it? Yeah, you should. So you know that T is what? Potential or kinetic? Kinetic energy, right? TATB should be half of MBA square plus. You know, you have the VA only the spring, right? TB should be half of MBB square, which is the potential energy, plus this BB spring plus this BBG, or for gravity, right? So you're gonna solve this equation and you should be finding the value of V. I do have the value somewhere. It's 1.96. See if you can find this value. BB, you should be finding this value 1.96. If you can find this value by yourself without any question so far, you're good to go. Very simple, straightforward problem. At two locations, we have this summation of forces. We're doing the energy balance. The summation of forces, whenever I'm saying that kinetic and potential energy, kinetic is very straightforward. It has something to do with the velocities, right? But the potential energy could have like spring force or the gravity force or other form of energy, right? So you're gonna be solving it for this problem at two locations, A and B. The challenge here to understand why the distance between A and B particle is 0.4 to understand from the graph or from the figure. Okay. If you understand that, then finding the gravity force is very straightforward. And the spring is also very challenging. Okay, you got to find the spring distance. I mean, now that I did solve it for you, it seems like a little easy, right? If you're gonna solve it by yourself, then it's not that easy. It's like this spring, how much of a stretch happened, how much of the compression happened, because it has something to do with the circular movement on the arc. It is a little tricky to understand. Okay, so just keep it in mind. Like the challenge out there. Okay. If we'll have time in next class, we're going to start talking with homework even from next class. Okay, but the idea is by this week should be able to finish homework number 8 with chapter 14 decisively. Okay, so we should be feeling confident about the exam next week. And the final exam I did say about the take home, right? So the third exam is actually your last exam what in between in class. So the progression of things happen on dynamics. If you recall, we started with the velocity, acceleration, and position, right? And then that was chapter 12. And then exam 2, we started focusing on the forces, right? All sorts of forces. And then in chapter 14, that was chapter 13. In chapter 14, we were seeing things with energy, right? And in chapter 15, you'll be seeing the momentum, impact, those things, okay? And that's pretty much it. So that will be your dynamics. You got the value, Christian? If you got the value, that's it. You know. Lauren, you're not getting the value?
I got some 3 something.
Yeah. That's what you got. Two of you?
Yeah, I'm not getting
I don't know. Christian, you got the right value? Now I'm questioning myself. What is I'm doing? Okay, so half of 4 kg multiplied VV squared. Okay, there is a, I think the catch is, all right, so okay, plus VA. I'm skipping the unit for now. I do have the result here written as 1.96 in my notes. Is that the value of card? Why? Like you have everything as it is shown. Uh, Did you know you calculated it? What value you got for VB? Alina, you got some value? Okay. I got a pitch in, I guess, at this point.
Yeah, I'm getting the same value as I did last time.
Like what?
3.44.
What about you, Alisa? Brad? 3.44?
Yeah.
Christian, how did you get 1.96?
I see what I did wrong. I used 60 instead of 18.
So I did wrong as well. Sorry about you guys. It's perfect. So 3.44 meter per second, right? Alain, you get the 3.44?
I didn't get that. I thought this was wrong.
I must have it wrong, but I'm gonna turn it. I'm gonna verify. Okay, and I'll leave you. Okay, so I don't know. I gotta verify. Let me do. Let me do some math. So I do have 16 means 8 plus 2 minus 18. I see. How do you get 11.44? Just 1 second. So can you do square root of 3.85? Everybody? Yeah, I had the square root of, yeah. You see what is happening here? This gravity is acting down. The G is acting down. So that is the only way. Alyssa, so this gravity 9.81 is acting down. So that's the reason. So this thing would be, this value would be negative here. So this become positive. So if you're going to do the math that way, it would be 1.96. Is that the value I wrote before?
Yeah.
Okay.
Change?
So the negative direction, the gravity is acting down.
So what changes in the numbers?
The number is like, I had 18 joule and minus, instead of minus 15.7, and I had a plus because the value of VB is negative.
Oh, I see.
Okay. Yeah, the result was, this was the correct. This is my bad. I forgot about the negative G. Understand? Does it make sense now? Because the G is acting down, right? I did mess up. I put the positive. All right. Okay, so I'll see you again on Wednesday, okay, everyone? You start solving the homework though. I have the problem for Wednesday is really small, probably finish up within 30 minutes. We can have like sometimes to talk about the homework, okay? Start solving the homework so we can use the whole class time, okay? If you guys want, I can go with some more theory so we can use more class time. I don't know. You guys read through the theory, right? A little bit. And I guess better use of time is like focus on the homework and come here talk with me about the homework.
Have a good day, Professor.
Okay, I'll see you guys. Or if you see Brody, anyone, let him know that I'm looking for him.